Welcome in geological knowledge. Today we will discuss a very important topic known as paleothermometry, and we all know that paleothermometry means the decipherance or the knowing about the ancient temperatures. Okay, and our discussion will our discussion will be dedicated to the tools for the estimating diagenetic paleotemperatures especially. Okay, and it's in your GSI mains syllabus, so we will discuss it in detail that what are the tools or the parameters which are very essential in deciphering or in investigating the paleo temperatures of diagenesis. Okay, so in that continuation of that we will start our today's discussion. Let's start. And before we start, so, estimating the diagenetic paleotemperatures, there have been considerable researches have been done, carried out to develop a reliable technique for the paleotemperature analysis. There have been several techniques which have been considered, and the research is going on still to evaluate or to decipher the paleotemperature analysis. And tools used for the determination of the paleotemperatures, they are known as geothermometry. Basically there are two terms, geothermometry and geobarometry. Okay, so geothermometry means the temperature, okay, and barometry means the pressure. So today's discussion is based on the geothermometry, means on the temperature. The primary techniques now in use for the determination of diagenetic paleotemperatures include the following methods. We will discuss them one by one. First one is very important and is extensively used, that is the conodont color alteration. So conodonts are marine microfossils composed mainly of the mineral apatite or the phosphatic minerals, and most important phosphatic mineral if we talk, that is the apatite. And if we talk about its chemical composition, that is Ca5PO4O3, but it can also contain some trace amounts of organic matters. Okay, so they range in age from Cambrian to Triassic period and occur principally in carbonate rocks as well as in shale rock. So their occurrences are in the carbonate rocks as well as the shale. But if we talk about the conodont range or their ages, so their age range from Cambrian to Triassic period. It's important to remember the age as well as the source rock or the host rock where they are occurring. And if we talk about the changes in the colors, so color changes in conodont from pale yellow to brown to black. So you have to remember the series, that what are the changes in the color on the basis of the temperature. So pale yellow is that when we talk about pale yellow, the temperature is less than 50 to 80 degrees Celsius. To brown, when it changes to brown color, its temperature changes from 60 to 140 degrees Celsius. To black, 300 to 400 degrees. So this temperature range as well as the color alteration is very important to decipher the diagenetic properties. Owing to the carbon fixation within the trace amounts of organic material in the conodonts as a result of the increase in the temperature. Okay, so color and the temperature ranges or the differences are very important. And extremely high temperatures may change the color to white. So the series be pale yellow to brown to black, and the extreme cases, extremely high temperatures, they change the color to white, that is extremely thermal alteration because of loss of carbon as well as water. And next one is vitrinite reflectance. So vitrinite is a structure of or unstructured woody tissue plants with impregnations that mainly occurs as disseminated grains in sediment and as a major constituent in the coals. When we were discussing about the constituents of the coals, microscopic and the uh, major macroscopic and the macroscopic constituents of the coal, we have discussed about the vitrinite. Okay, so that is a woody tissue plant that is impregnated, that occurs as a disseminated grains in sediments as a major constituents in the coals. So it's also used, and their reflectance is used. So light reflection from the vitrinite thermally altered organic grain is measured quantitatively with a reflectance microscope. And what happens in reflectance microscope, the reflection increases with the increasing degree of the thermal alteration or the metamorphism process. So as soon as the reflection increases, the increasing degree of thermal alteration also grows or increases, and up to about 240 degrees percent vitrinite reflectance is related to minimum temperature by a scale that range from 0.48% at less than 100 degrees to 2.14% at 240 degrees Celsius. So this temperature range as well as the percent is very important. That scale ranges from 0.48% at less than 100 degrees Celsius to 2.14% at 240 degrees Celsius. Okay, so this temperature range is also important, and this has to keep in mind that reflection increases with the increasing degree of thermal alteration. Okay, and next tool is graphitization level in the Kerogen. So Kerogen, which occurs principally in the seals, is the dissemination organic matter of sedimentary rocks, which is insoluble in non-oxidizing acids, bases and organic solvents. So that is the disseminated organic matter of sedimentary rocks, which is insoluble in the non-oxidizing acids, bases and organic solvents. And organic matters initially deposited in sediments, they are converted to Kerogen during diagenesis process because of the thermocatalytic processes. Okay. The carbon atoms in the Kerogen becomes increasingly well ordered or the well structured in increasing levels of the thermal diagenesis. So what happens, जो carbon atoms हैं, those carbon atoms in Kerogen, they become increasingly well ordered or the well structured because of the increasing level of thermal diagenesis. So that process is known as graphitization. Okay, the increasing level of thermal diagenesis because of the carbon atoms becoming increasingly well ordered. So that process is known as graphitization, and that is very important process. An increase in the degree of ordering or the level of graphitization determined by X-ray diffraction, okay, or better known as XRD method, can be related to increase in the diagenetic temperature. And the temperature range is very important in all the methods. The method can be used to estimate the temperatures in the range of 400 to 600 to 650 degrees Celsius. So that temperature range is very important. And another very important technique, that is analysis of clay mineral assemblages. So clay minerals are most abundant in seals, but accumulates as a but they occurs also as a matrix in the sandstone and minor amounts in the limestone. Okay, so basically they are abundant in the seals, but they can also occur as a matrix in the sandstone and minor amounts in the limestone, mainly in the fossiliferous limestone or other fossils. Sorry, in the other limestones. And what happens during the process? So with the increasing temperature and metamorphic grade, smectite clay minerals convert to illite through a mixed layer illite smectite series. So smectite clay minerals, they convert to illite through a mixed layer illite smectite series. Chlorite appears as well as kaolinite as well as potassium feldspar disappears. So during that illite smectite series process, chlorite appears, but the kaolinite, also known as potash feldspar, that appears. So this is important, that chloride appears as well as kaolinite disappears. Thus, the relative abundance of these clay minerals in the rocks can be related to paleo temperature, that is, smectite occurs at temperature below about 100 degrees, and mixed layer clays are stable up to about 200 degrees, and illite form at a temperature above 200 degrees. So that temperature range is very important. Means smectites below about 100 degrees and mixed layer clays at about 200 degrees, and illite forms at temperatures above 200 degrees. So the useful temperature range of the method is up to 300 degrees. Okay, because the maximum temperature that ranges, that is in illite, which is about 200 degrees. So we can uh, use this method in order to uh, calculate the temperature range up to 300 degrees, not more than that. Another important tool, that is the analysis of zeolite facies mineral assemblages. So zeolite facies minerals are orthogenically in volcanic clastic sediments through alteration of chemically reactive volcanic materials. Okay, so they are orthogenically in the volcanoclastic sediments, and they form in the overlapping temperature ranges of diagenesis and metamorphism, as and show a progression of mineral facies, that is a reflection of temperature and pressure of burial. Okay, so that is the most important tool, that is the analysis of the geolite facies. Okay, because the facies, metamorphic facies, starts at the lower temperature in the form of geolite facies. So there is a very minute boundary which distinguish between geolite facies or the metamorphic facies to the diagenesis. Okay, so that ranges, they show range of diagenesis and metamorphism and show a progression of the mineral facies, that is a reflection of temperature as well as pressure of the burial temperature and pressure. And if we talk about the temperatures, so theoretically exerts a strong control of the types of zeolite minerals that occur together. And if we talk about the major minerals which occur, so for example, heulandite and anaclite tend to form at temperature below about 100 to 125 degrees, whereas lomonite and pumpelite form at temperatures between 100 to 125 degrees and 175 to 200 degrees. So at one hand, hollandite as well as anaclite, they tend to form at a temperature range about 100 to 125, as well as lomontite and pumpelite, they form at the temperature range of 100 to 125 and 175 to 200 degrees. So the temperature ranges up to 200 degrees to 250 degrees can be established roughly on the basis of the assemblages of geolite facies minerals. And the minerals, they are present in the rock, they can be heulandite, anaclite, lomontite and the pumpelite. So on that basis, the temperature ranges we have discussed, we can calculate the diagenetic temperatures. Okay, and next very important tool, that is the analysis of fluid inclusions. So this is very important. Fluid inclusions occur in a variety of sedimentary rocks, sedimentary materials. Okay, they can be in the form of geodes, wooks in sediments, sedimentary ore deposits, carbonate and quartz sediments in sedimentary rocks, salt and sulfur deposits, petroleum reservoir rocks, as well as sphalerite, which is the zinc bearing ore mineral, and in the bituminous coal beds. So these are the uh, agents where the fluid inclusion can take place in the sedimentary material. Okay, and recrystallization process of mineral or formation of overgrowths on mineral due to diagenesis may trap fluids as minute inclusions in the crystals. Okay, so जो crystallization की process है in the mineral formation of the overgrowths on a mineral during the diagenesic process, they can trap the fluids, and they are important, very important, in order to define the paleo temperatures. Okay, and fluid inclusions commonly consist of fluid as well as the bubble of gas. So L plus G means liquids plus bubble of gases. Presumably the inclusion consisted of a single fluid phase at the time of formation, which separated into two phases upon cooling. What happens that the inclusion consists of a single fluid phase at the time of its formation, but after some time which is separated into two phases upon cooling. So by reheating the mineral until the phase boundary between the liquid as well as gas can be seen to just disappear, the approximation temperatures at which the inclusion form can be established, taking into account an estimate of the pressure of the formation. Okay, so by the process of reheating, what happens, reheating process में जो minerals हैं, they can be reheated until their phase boundary between the liquid as well as gas is seen to disappear. So the approximate temperatures at which the inclusion formed can be established, taking in account the estimate of the pressure of the formation of those inclusions. So the method is useful at temperature range from 25 to 150 to 200 degrees Celsius. Okay, so that range is very important, up to 25 to 150 to 200 degrees Celsius. And another very important method tool, that is oxygen isotopes. So we know that the fractionation factor between two coexisting minerals is defined as alpha AB, that is the ratio of O18 to O16 in A and O18 to O16 in the B. In these two refer the two oxygen containing minerals. Okay, where A and B, they refers the two oxygen containing minerals. So oxygen O18 to O16 ratio in A with the oxygen O18 to O16 ratio in the B. So the ratio of O18 to O16 into coexisting oxygen bearing minerals from the same specimen. This is very important, that the specimen should be same. The ratio of O18 to O16 will be taken in the two coexisting oxygen bearing minerals. They should be formed at the same specimen, such as quartz and elite is commonly different. Okay, so the amount of this difference has been shown to be a function of the maximum temperature to which the rock containing the mineral was heated during the diagenesis. Okay, so जो function है of the maximum temperature to which the rock containing the minerals was heated during the diagenesic process or the diagenetic process. So therefore the isotopic fractionation, or the difference between O18 to O16 ratios of these two minerals that have reached up to the equilibrium condition with each other, can be used to calculate the maximum diagenetic temperature to which the rock was heated. Okay, so that oxygen O18 to O16 ratio of two minerals that have reached up to the equilibrium, they are used as a calculate to calculate the maximum diagenetic temperature to which the rock was subjected or rock was heated. For example, isotopic fractionation between quartz and illite pairs is greatest at low temperatures and decreases with the increasing temperature. So the method is useful to the temperature range of about 400 degrees Celsius. Okay. So that was our discussion about the paleotemperature, diagenetic paleotemperatures, and that is very important in order to calculate the paleotemperatures. Okay. Thank you.